Okay, so I have 2 chloropropane, 3 carbons. Position number 2, I have a chlorine, this green one. So instead of having a nucleophile, I have an hydroxide ion. Oxygen, hydrogen, extra pair of electrons, negatively charged. Now, the hydroxide ion, in this case, is not acting like a nucleophile. So it isn't exactly very stable. It's very impatient and it wants to get neutralized. So the way it will neutralize is not by attacking a positive carbon, but simply by grabbing a proton or a hydrogen. Now, the question is, which hydrogen will my hydroxide grab? The answer, you might think, would be the hydrogen right where your leaving group is. So this is the carbon in the middle, leaving group, chlorine, proton next to it. No, that's not the case. Okay? So, the E2 reaction, which this is similar to the SN2 reaction in that it's a backside attack of sorts, but we're not attacking the backside of the carbon, we're attacking the backside of the carbon adjacent to it. What do I mean? Okay, so let's look at our model, our substrate. Okay, let's do a Newman projection. Okay, so here, Newman projection. Okay, there. The carbon in the front has this leaving group. Okay, oops, there. And the carbon in the back, this one, has a hydrogen in the anti-position to my leaving group. Okay? So yan, trans-like, anti sila. Okay? They're anti. There. Okay? The hydroxide will use its extra pair of electrons and it will grab this anti-hydrogen. Okay? So it will take this hydrogen. Now, the hydroxide is water, stable. Okay? This carbon, these extra electrons will now become a pi bond here in the middle. Okay? And since this carbon cannot take 5 bonds, it will release the leaving group. So the chloride ion will fly away. Like that. And then, voila. You now have an alkene there. Okay? So it was an elimination reaction. Okay. So this is an E2 reaction. So it's similar to an SN2, but instead of a nucleophile, we used a strong base. And there. Okay? So we end up with an elimination product. So again, important that, our leaving group and our proton that was removed by the base are in that anti-position in a Newman projection. So again, anti, okay? Again, leaving group, anti to the proton taken by the base. Okay? There. Now, when doing this reaction, it's important that you actually draw Newman projections so that you can determine the stereochemistry of your product. What do I mean, stereochemistry? Since you're forming an alkene product, then you have to know, will my product be E or Z, cis or trans, okay? And that's what drawing the Newman projection helps you to do. So let me get my board. Okay. Tissue. Okay. Okay. So, okay, carbon in the front, carbon in the back. Carbon in the front can have either your leaving group or your proton. So in our case, let's put the proton, H. So anti to it should be your leaving group. Okay. Now, when you're taking your exam, okay, you cannot just choose where to put everything. You actually have to follow the structures given to you. And it's your job to twist. Okay, let's pretend given to you in the exam is something like this. Okay, it's your task to make sure to find a way to rotate it. Okay, so that you can keep, let's pretend these are chiral, then you have to make sure you're dealing with the same structure. So you have to do the Newman projection and twist it in your minds properly, okay? Until you end up with your proton of interest and your leaving group in the anti-position. And the rest, A, B, C, D, okay, will have their own places in the Newman projection. The base, again, takes the proton. These electrons that was once bound or used as the bond to the proton now becomes a pi bond here in the middle. Okay. And then these electrons go to the leaving group. Okay. So that the leaving group can leave, let's say the chlorine can leave as a chloride ion. So it leaves as an anion. Okay. Now, what happens is that this disappears, and you end up with an alkene product. And what is my alkene product? Okay, this is the view of our alkene product. Okay, in fact, it's no longer bent, but all on the same plane. Okay, so ganyan, you're gonna draw it like this. Okay, okay, how do you interpret this? Let's draw an alkene. Okay, let's put this side as the dot side, and this side as the circle side. In the dot side, okay, in the left side, you have a carbon. So let's pretend this is us. I'll draw a stick figure person there looking. So on that side, this is his left. It will be the carbon, the C, sorry. And then on this side, it will be the D. Okay? And then the ring side, the back side, to the left will be the A, and to his right will be the B. So that's how you interpret this Newman projection. And this is the equivalent alkene product of the E2 reaction. Okay? So, the beauty of using a Newman projection for predicting your E2 reaction is that once you do that, you remove your proton, your leaving group, anti from each other. The rest, you can simply flatten out. And you can see that A and C are cis to each other, same side. B and D are on the same side. A and D are trans to each other. B and C are also trans to each other. See? So this alkene is the correct alkene. That's how you do E2 using Newman projections.